For decades, the blueprint for the world's fastest supercomputers has remained largely unchanged. Take a powerful central processors, pair them with massive arrays of GPU accelerators, link everything through a high-speed network, and let those GPUs handle the heavy mathematical lifting that would bring standard CPUs to their knees. America's Capitan follows this exact formula of pairing AMD server chips with MI300A accelerators to deliver over 1 quintillion calculations per second. That machine held the top spot on the global supercomputer rankings until now. A previously unlisted Chinese system called Lianxin has entered the official top 500 list straight at number 1. Its verified performance sits at 2.198 exaflops compared to El Capitan's 1.809, putting the Chinese machine roughly 21.5% ahead on the benchmark that determines the global ranking. But the performance gap isn't even the most surprising part. What makes this story remarkable is how Lianxin got there. Lianxin crossed the 2x flop threshold without a single dedicated GPU accelerator, no NVIDIA hardware, no AMD Instinct cards, no Intel data center GPUs. Instead, the machine relies on millions of custom Chinese CPU cores, a proprietary interconnection network, and a fully domestic software stack, making it the first publicly ranked supercomputer to sustain over 2 exaflops using CPUs alone. This doesn't mean GPUs are suddenly obsolete, and it doesn't automatically crown Lianxin as the superior AI computing platform. A single benchmark can't capture every real-world workload. But the result is official. China has reclaimed the #1 supercomputing position for the first time since 2017, and it did so by rejecting the architectural approach used by nearly every other leading machine on the planet. The top 500 list has tracked the world's most powerful publicly disclosed supercomputers since 1993, updated twice a year. Systems earn their ranking by running a test called High Performance LinPack, or HPLA benchmark that challenges machines to solve massive systems of dense linear equations using high-precision 64-bit floating-point arithmetic. Lianxin's submitted figure of 2.198 exaflops isn't a theoretical ceiling. Its peak theoretical performance is actually higher, around 2.736 exaflops. The fact that it achieved roughly 80% of that theoretical maximum during the benchmark is one of the most telling details in this entire story. Building millions of processor cores is one challenge. Keeping all of them productive simultaneously is a different problem entirely. Processors don't just compute, they communicate, share data, and synchronize across a single enormous problem. If that coordination breaks down, adding more cores can actually make a system slower. An 80% efficiency rating signals that Lianxin's architecture is not just large, it's genuinely well organized. Lianxin is installed at the National Supercomputing Center in Shenzhen and was developed around a custom platform called Lingkun. Its central processor is the LX2, a Chinese-designed chip packing 304 cores running at 1.55 gigahertz. Across the full system, that adds up to 13,789,440 cores spread across roughly 45,360 processors. That clock speed might sound unimpressive next to a consumer desktop chip capable of exceeding 5 gigahertz, but supercomputers aren't built to push a single core as fast as possible. They're built to make millions of cores work in concert. At this scale, power efficiency, parallelism, and communication architecture matter far more than raw clock speed. Think of it like moving a mountain. One extraordinarily powerful worker can't do it, but 45,000 organized teams can, provided each one knows exactly what to move, where to put it, and when to act. Without tight coordination, more workers just means more chaos. Every processor in a supercomputer depends on data from elsewhere in the system. When results travel slowly, processors sit idle. At exascale, even tiny communication delays, repeated trillions of times, compound into serious bottlenecks. Lianshin addresses this through a proprietary Chinese interconnect called Lingqi. Technical details about it remain limited, but the benchmark results speak clearly. This network is doing serious work. Lianshin also claimed first place on a second benchmark called HPCG, High Performance Conjugate Gradients. Unlike HPL, HPCG stresses memory access patterns, data movement, and irregular communication, the aspects of supercomputing that most often prevent theoretical speeds from translating into practical ones. Lianshin posted around 22 petaflops on HPCG. El Capitan managed roughly 17.4 petaflops, placing the Chinese system about 26% ahead on this second measure. This result undermines the easiest criticism of the HPL result. Lianshin didn't simply win one highly optimized matrix test and then fall apart under more demanding conditions. It led both benchmarks, suggesting its interconnect and memory. Subsystems are genuinely capable of keeping nearly 14 million cores well supplied with data. GPUs became dominant in supercomputing for clear, logical reasons. A CPU handles diverse instruction types, operating system tasks, branching logic, serial code. A GPU is far narrower but massively parallel, excelling when identical operations must be applied across enormous data arrays. Scientific simulations and neural network training are full of exactly those operations. So why would any team building a world-class machine deliberately avoid them? One answer is programming simplicity. Accelerated systems force developers to split their applications between CPU and GPU, move data between separate memory spaces, and tune code for specialized hardware. A CPU-based system offers a more uniform environment. The same processor type handles more of the work, reducing the architectural divide even if the scale itself remains challenging. CPU architectures can also handle workloads involving complex control logic or irregular memory access patterns that don't map efficiently onto GPU hardware. The trade-off is raw energy efficiency. GPUs produce significantly more parallel arithmetic per watt on suitable tasks. To compete without them, Lianshin needed to deploy an extraordinary number of cores and keep them highly utilized. It succeeded, but at a cost. What makes Lianshin especially significant beyond its GPU-free approach is how thoroughly Chinese the entire system is. The LX2 processors are custom-designed domestically, and the platform is Lingkun. The interconnect is Lingqi. The operating system is Capitan. The benchmark submission also references a locally adapted compiler and customized mathematical libraries. This matters because supercomputer performance doesn't live in silicon alone. A powerful chip running poorly optimized code wastes most of its potential. The compiler, mathematical libraries, operating system, and networking software all need to work together efficiently. When a system achieves 80% of theoretical peak, that usually means multiple layers have been co-developed and tuned as one integrated system. China didn't build a novel processor and drop it into an existing Western supercomputer design. It submitted a complete, homegrown platform capable of leading the world's two most prominent supercomputing benchmarks. Simultaneously, there is a real trade-off worth acknowledging. Lianshin draws approximately 42.2 megawatts under load, minus industrial-scale power consumption. That represents a serious operational cost and cooling challenge. On energy efficiency, El Capitan holds the edge. The American system delivers around 60.94 gigaflops per watt. Lianshin achieves approximately 52.07 gigaflops per watt, making El Capitan roughly 17% more efficient on that metric. This is where the accelerator advantage becomes visible. Lianshin wins on raw HPL performance. El Capitan extracts more computation from each watt. Here's the most important caveat. Shift the benchmark toward the lower precision mathematics that powers modern AI, and the ranking flips entirely. The HPL-MXP benchmark measures next precision performance, the kind of calculation used heavily in machine learning workloads. Lianshin achieved roughly 7.92 exaflops on HPL-MXP and ranked fourth. El Capitan achieved 16.7 exaflops and remained number one, delivering more than twice Lianshin's result. This is why context matters so much when discussing the world's fastest supercomputer. Lianshin leads on the traditional benchmark that has defined the top 500 ranking for over 3 decades. It does not lead when the work resembles training a large AI model. For that kind of computation, GPU-accelerated systems hold a commanding advantage. The two machines are genuinely different tools. Lianshin is a high-precision freight engine built for large-scale scientific workloads. El Capitan is a more versatile hybrid with specialized hardware suited for different types of computation. Before Lianshin appeared, the top positions on the top 500 were an American clean sweep, El Capitan first, Frontier second, and Aurora third. The United States had established a clear lead in publicly ranked exascale computing. Lianshin didn't gradually climb the rankings. It appeared directly at number one. That shifts the official performance lead back to China for the first time in nearly a decade. And it expands what an exascale machine is understood to look like. The industry had broadly concluded that GPU accelerators were essentially mandatory at this performance tier. Lianshin demonstrates that a CPU-only strategy can still win the traditional crown, though the power demands are substantial. The AI performance lags significantly, and many architectural specifics remain proprietary. The most important takeaway from Lianshin isn't the ranking itself, it's the architectural divergence it represents. China didn't win by building a slightly larger version of El Capitan. It took a fundamentally different road, distributing computation across nearly 14 million custom CPU cores, paired with a network capable of keeping all of them synchronized at exascale. That approach required processors, networking, software, and system architecture to be designed together around a single objective. The result is a machine that behaves less like a collection of separate components and more like one enormous, tightly engineered instrument. The CPU is supposed to become a supporting actor in the exascale era. Lianshin put millions of CPUs at the center of the stage and reached number one.